In this first video for Chapter 8, we're going to look at the method outlined in Section 2 of the chapter, which is called integration by parts. So we've said several times before that there's not a product rule for integrals, but there for certain types of products under the integral sign, we can use this method to resolve the integral. So let's actually start with the product rule, which is the derivative with respect to x of u times v, and we know that that is the first times the derivative of the second plus the derivative of the first times the second. And if we multiply everything through by dx, we get d of uv equals u dv plus v du. And then let's integrate both sides of this equation. So we integrate this first term this term on the left, integral and derivative undo each other, so we just get uv on that side, and so uv equals the integral of u dv. So we get this formula, which we're going to write in a slightly different form. The integral of u dv equals, so we're solving for this term, and we get that if we solve for that, that equals uv minus the integral of v du. Let's put a box around that. Now, so why is this formula useful? It turns out that for certain kinds of products u dv, we can resolve the integrals sometimes very quickly, sometimes it takes a couple of steps. So let's divide the types of integrals we can do using this technique into three categories. So let's say that we have type 1 integration by parts when we are integrating, or when the integral is a polynomial function multiplied by either an exponential or a trig function. When we have an integral of that type, we can always set u equal to the polynomial function and dv equal to the exponential or the trig function. So let's do example 1 on page 163, the integral of x times cosine x dx. So as we said, u would be the polynomial function, so our u is going to be x, and our dv is going to be the remainder of what's under the integral sign, cosine x dx. So the dv is our cosine x dx. But to resolve the integral on the right hand side, or to resolve it into a new structure and apply the parts formula, we're going to want to write this as uv minus the integral of v du. So we've got u and we've got dv, but we need to find v and du. So let's find v and du. And the way we find v and du, well, we've got u, so du would just be its derivative of x, which would be dx, and to get v from dv, we integrate what dv is, and that gives us sine x. So we have all of the elements that we need. So let's put them together. So the u is x, and the v is sine x, And then we've got minus the integral of v, which is sine x, and du is dx. So did we accomplish anything in rewriting the integral in this new structure? Yes, definitely we did, because now the integral is the integral of sine x, which we can do. Let's go back a step and go and look at the original integral. You might be asking the question, oh, why go to all this trouble? We know that the integral of x is x squared over 2, and the integral of cosine x is sine x. So why do you have to use this formula? The answer is that you cannot integrate a product. There's not a product rule. You have to rewrite that product or use some formula like this parts formula to resolve it. So we can't integrate x cosine x outright, but we can turn it into this new structure here, and that new structure is easy to integrate, right? The x sine x is already outside of the integral, and when we integrate sine x, we get minus cosine x. There's a cosine x, or there's a minus sign out front, so it's plus cosine x, and so here is our answer. We should differentiate this to confirm. So it's x sine x plus cosine x, and the derivative of that, so the product rule of the first gives us x cosine x, that's first times derivative of second, plus derivative of first times second, plus the derivative of cosine x, which is minus sine x. We get back to x cosine x, which was our integrand. Notice if we did it that other way, x squared over 2 sine x, and we start differentiating that, we can see we're not going to get very far, right? We get x sine x, that's derivative first times second, plus x squared over 2 cosine x, and that's as far as we get. So clearly this integrating a product without using any special formula doesn't work. Let's go to a slightly more complex example. Example 2 on this page, where we're integrating x squared cosine x dx. Is it just as easy as the previous one? Well, again, we let u equal the polynomial part, we let dv equal the trig or the exponential part, we calculate the du and the v, the du by integrating to x dx, or by differentiating the v from the dv by integrating. We apply it into the parts formula, or we plug it into the parts formula, uv minus the integral v du, and we get x squared sine x minus the integral of v times du, which is 2x sine sine x dx. Now we've got an integral that has a product under it still. So we haven't, on first step, gotten an integral that we can do, but we're just able to apply the parts formula again. So x squared sine x, bring the 2 out front, x sine x is the integral we're trying to resolve, and we just set up parts again. U is x, dv is sine x, du is dx, and v is minus cosine x. Plug everything into the parts formula, and so we've got, already have the x squared sine x minus 2, and then we've got minus 2 with a new uv minus the integral of v du. The v is x times minus cosine x plus or minus the integral of v du, is this. And then we see that we can resolve everything, right? The x squared sine x stays the same. We distribute this minus 2 across, and we get 2x cosine x, and we distribute the minus 2 across here, which is going to give us minus 2 sine x plus c. So here is our answer for this problem, which is same formula, integration by parts, but we had to do it in 2 steps, and so we can actually generalize and say that if we have the integral of x to the n times a trig or an exponential function, that we're going to still let u equal the polynomial part, but we're going to have to do parts n times. Right, and just now that we've done integration by parts a couple times, we can see what we mean by the parts, right? The parts are the factors under the integral sign, and we have to divide them up in a special way, or we won't be able to. It doesn't always work if we pick any u or any dv. If we reverse this process and made v be equal, or dv x squared and u cosine x, it wouldn't work. Okay, now let's go to a part 2 integration by parts. Or I'm sorry, type 2. When we have a I'm sorry, not polynomial, that's what we just did. We have a logarithmic function times a polynomial. And in this case, we do not, we reverse it or make it different than last time. In this case, the u is the logarithmic part and the dv is the polynomial part. So we look at example 3 on page 164, the integral of x squared ln x dx. We're going to let u be ln x, and dv would be x squared, and when we compute the du, we get what, dx over x, and we compute the v by integrating and get x cubed over 3. So we plug this into the parts formula and get u, v, which is x cubed ln x over 3, minus the integral of v du, and you can see that we're going to be able to do this integral because we're just integrating a polynomial. So if we rewrite this, we get what? X cubed ln x over 3. Bring this 3 out, minus 1/3. We're integrating x squared dx. And so that's going to give us x cubed over 3. So we get x cubed ln x over 3 minus 1/3 x cubed over 3 plus c. And we can simplify that second term to make it x cubed over 9 plus c. Notice that in example 4 on this same page, that when we have the logarithmic function raised to a power, then u is that, but we're going to have to do parts twice to do that. And if you look through the steps of this example on page 164, you see how this one is done twice. So sort of like the part one that we did twice. So now let's go to integration by parts type 3. Type 3 is when we have a exponential function times a trig function. And we should just make note right from the start that we're going to have to do this twice every time. And so if we look at example 5 on page 165, let's see how to do that. Let's start with a whole new blackboard for this. So we've got e to the 2x cosine 3x dx. And we actually have a choice what is u and what is dv, but I'm just going to pick them in order. We're going to do it twice. We have to stay consistent in which part is u and which part is dv. So we picked u to be the exponential part and v dv to be the trigonometric part. We have to stay consistent. So we're differentiating the exponential function, which is the function itself times the derivative of the power. The integral of the cosine function is the sine, and we divide by the derivative of 3x. So uv minus the integral v du is going to be e to the 2x sine 3x over 3 minus, and then it's v du. Du has has a 2 multiplier, and v has an over 3, so let's bring that out, both those out, minus 2/3. And then we've got e to the 2x and v du and sine 3x dx. So we have to set it up again as a uv. So u is e to the 2x again, and dv is sine 3x this time. Du is still again 2 e to the 2x, and v is minus cosine of 3x over 3. So if we bring that across, we get this term right here is repeated. And then for this term right here, we're going to put the 2/3 out front, and then put in the new u v minus the integral v du. And remember, the u was e to the 2x and the v, so it was e to the 2x and minus cosine 3x over 3. Let's make sure we designate that as a minus sign right there. And then the integral of v du is e to the 2x or 2e to the 2x and minus cosine uh, 3x over 3 dx, and that was minus. So let's set this equal to our original function, which was here. e to the 2x cosine 3x. So we start off with e to the 2x cosine 3x dx. We got e to the 2x sine 3x over 3. We've got this part right here, which is plus 2 over 9 e to the 2x cosine 3x over 9. And then we've got the minus 2/3 times this, and we've got a 2 here and in the numerator and a 3 in the denominator, so that's minus 4, let's see, minus, so it's 3 minus signs. So minus 4 ninths integral of e to the 2x cosine 3x dx. Is this good or bad? We wound up with the integral that we started with is showing up on the right hand side. Are we going around in circles? Well, if the coefficients of these were the same, yes, we would, or we would get something that's not an equation. But what we're able to do here is notice that what we have is something that looks like this. X equals a plus b minus 4 ninths x. And so we can say that 13 ninths x equals a plus b, x equals 9/13 a plus b. So that's what we're going to do. We're going to say that we have 13 over 9 times the integral of e to the 2x cosine 3x dx, which we get by combining this and moving this term over to the left, and that equals e to the 2x sine 3x over 3 so we get this, and then we can just multiply both sides by 9/13, and so the 9 is going to change this numerator here to a 3 and change this numerator here to a 2. So, and then the denominator of both is going to be 13. So here's what we get. So we did parts twice. We wound up with the same integral on both sides, but it had a different coefficient, so we could bring it back over and do a little bit of algebra and solve for it. It's always the case when we do these problems that whatever coefficient we have here shows up in front of one of these terms, and whatever coefficient we have here shows up in front of the other, and the denominator is always the sum of the squares of those two coefficients, which in this case is 13. These problems are a little bit harder, and there will be some problems like this on the exam, but not all of them will be of this degree of difficulty. So we've done 3 integration by parts of 3 different types. Let's just quickly go back and review the types. First type, we had a polynomial times an exponential function. In that case, or polynomial times exponential and trig. In that case, u is always the polynomial, and dv is always the trig or the exponential. If that polynomial is raised to the first power, we can do it only need to do this parts technique once. If the polynomial is raised to a second power, we have to do the parts technique twice, and if it's raised to the nth power, we have to do the parts technique n times. I wouldn't put one on a test where you have to do it more than twice. Type 2, we have a logarithmic function times a polynomial function. This time, u is the logarithmic function and dv is the polynomial function. And they are about the same level of difficulty as type 1. And we may have to do it more than once if the logarithmic function is to a higher power, such as it is in this example. And then the final type that we discuss is when we have an exponential times a trig function. We always have to do these twice, and what is unique about these or distinctive about these is that the integral that we start with, the integrand that we start with winds up being the same integrand on the right-hand side of an equation after we've done this twice, but we start off with a coefficient of 1, and we, on the right-hand side, have some other coefficient, and we're able to then combine this together to get a new coefficient in front of our original integral. That new coefficient is actually going to be the sum of the squares of that and that divided by, and that's not always possible to figure out what's divided by, but anyway, we can resolve this integral by then dividing through by this this coefficient right here to find our result. To find the result for this integral, and knowing that, as noted, we'll know what coefficient will be here, and here will be coming from what was here, and then that denominator will always be the sum of the squares of whatever these coefficients are here and here. So this is going to conclude this video on section 8.2, integration by parts.